Hello. Hello, Professor Manjunath.
Hi. How are you?
Hello, good. How are you?
Okay. Yeah. So let me. Yeah. So I just. Yeah. It took me a minute to find where the link was. Yeah. I forgot.
No.
So should I just share and see? Share,
Yes.
share screen or what?
Yeah, sure. Can I have to give you 1 second?
I think it is allowing me. Oh, okay.
No, 1 second. Yeah. Now it should be okay.
Yeah. 1 second. Let me. Where is that? Huh. So where is the? Okay. So should I share? Oh, I see. I share the particular application. Okay. But if I want to write something, I also wanted to share OneNote just in case. Can I share two applications or should I share screen?
It's 3 o'clock.
Hello?
So you want to write something on the...
No, in case, yeah, it may be necessary sometimes.
So what do you want to share? I mean, we can try that now.
No. I mean, anyway, so it is just a OneNote. If I need, I will write on this. That's all. Okay, let me see if I. But where is the? It says new share. Okay. This is also there. So which one do you see now? Do you see both?
Only one, the second one, where you can write.
Oh, I see. Okay. So mainly I will need the other one. So or should I share screen or what should I do?
You can share your entire screen. It will be easier, less time taking.
Yeah, but okay. Let me stop share. But yeah, I don't understand exactly how this is. Okay. So share screen. Share screen. Shall I just share the desktop or what? I mean, it gives me a lot of options.
Desktop one.
Desktop one. Okay. Okay. Then I have to bring the.
Yes, now we can see your entire screen. Whatever is going on in your screen, we can see it.
Now do you see the presentation?
Yes.
Okay, fine. All right. So I'll probably turn off the video when during the talk because of the internet issue.
Okay. Okay. So should we start now?
Yeah, sure.
Okay. Okay. And so a very warm welcome to all the participants of webinar on PDE and related areas. It is my privilege to introduce our speaker today, Professor Manjunath Krishnapur from Indian Institute of Science, Bangalore. Professor Krishnapur did his PhD from University of California under the supervision of Professor Yuval Perez. His research interests are in the area of probability theory and stochastic processes. He has several important publications in this field in prestigious journals like Annals of Mathematics, Communication in Pure and Applied Mathematics, and several others. I encourage everyone to go through his webpage, where a lot of important study material is available, including his book, Zeros of Gaussian, Analytic Function and Determinantal Point Processes. And today he will be speaking on the random plane wave and related objects. Professor Manjunath, it's over to you now.
Thank you. Thank you, Prasenjit, for this invitation. And I have seen the lecture series. It's running really well, it looks like. Yeah, so thank you very much for asking me here. So I'll just turn off the video. Yeah, okay. So, but I must say that having seen all the talks and so on, I told this to Prasenjit when he invited me, and it's now confirmed I am an odd person out in this seminar series very clearly, because the PDE connection is okay. There is a PDE connection, but I'm not a PDE person, and so on. So I'm a probabilist. So, but there is a PDE connection, of whether there is or not, one has to see. So let me anyway speak about it. So please feel free to interrupt me at any time actually. So it's okay, whatever I plan, it doesn't matter. You can interrupt me and ask questions. I may not see it, so you can interrupt me if needed. Okay, what is this study of? So let me just indicate. So it starts with, okay, there is a PDE. So the Laplacian is there. So let me recall the Laplacian and its spectra. So Laplacian on a, first on Laplacian on R2, just I stay with planar domains and manifolds. So Laplacian, we all know the Laplacian, and for the plane, the Laplacian eigenfunctions, so to speak, are these complex exponentials with these things. In a general compact Riemannian manifold, there is a Laplace-Beltrami operator, and it's a fact that it has a orthonormal basis of eigenfunctions. It has a discrete spectrum, and negative Laplacian is a positive semi-definite operator. So its eigenvalues start with 0, and then there's E1, E2. This should be E2, E3, and so on. Yeah, so E1, E2, E3, etc. With corresponding eigenfunctions, they form a orthonormal basis for the L2 of the manifold. Okay, so it has a long, there has long been interest in this object, especially study of eigenvalue asymptotics are kind of known. Of course, there are questions there also, but understanding eigenfunctions is also something of great interest. So what about the eigenfunctions? So what happens when to these eigenfunctions when you take very, very large eigenvalues? When En goes to infinity, what happens to, what do these eigenfunctions look like? That is a question. So for example, one of the things is this mod psi n squared. It is in many cases, it becomes uniformly distributed on a manifold. That is related to this quantum unique ergodicity and related matters. But there are other type of things that we are interested in. So one of the quickest way to know the profile of a function, we don't know what this function looks like, they can be complicated, is people study, the simplest one is where is it positive, where is it negative, right? So that gives an understanding of the function. So one is often studying, for example, the nodal set of this function psi n. So psi will be some psi n, and then you look at the set where it vanishes. Those are the level lines. Or you look at the complement of this, which may consist of a bunch of connected components. They are called nodal domains. I have some pictures shortly. So as I'll show, so this is what one has been interested in, and a lot of studies there on this kind of subject. But for the purpose of this talk, general manifolds are not needed. We stick to the sphere S2, two-dimensional sphere, and the two-dimensional torus, and the plane R2. They all the random, the functions we consider will be on these three spaces. Okay. Okay, so here is a picture. This is a two-dimensional sphere, and it is known that on the two-dimensional sphere, the eigenfunctions, they are called spherical harmonics, and the eigenvalues of the negative Laplacian are of the form n into n plus 1, as n goes over was 0, 1, 2, 3, and so on. Okay, so these are the eigenvalues, but they are not simple. So they have degeneracies. So the eigenvalue n into eigenvalue n into n plus 1 has a multiplicity of 2n plus 1. Okay, by the so I hope this is kind of, is it clear? When I highlight something, you can see it, right? Okay, so I am pointing sometimes by highlighting stuff.
Yeah,
so,
we can see. We can see.
Okay, so the distinct eigenvalues are n into n plus 1. So, and the multiplicity of that eigenvalue is 2n plus 1. So, these are called spherical harmonics. So, degree n spherical harmonics are those in this space, vector space of 2n plus 1 dimensions. Okay, and what is shown here is a picture by Alex Barnett of a some rather high n. I don't know what value it was. The picture shows the black is where the function is negative and white is where it is positive. Okay, so there is black and white, and this you see quite a complicated picture there. And this is particularly a random spherical harmonic, as I'm going to define shortly. Okay, so this is how the eigenvalues and eigenfunctions are like on the sphere. The other case that I said we are going to consider is the two-dimensional torus, which is just the unit square. Think of it as the unit square with the identification. So periodic functions on 0, 1 square. So the eigenfunctions are cosines and sines like this, cosine 2 pi px plus qy, or sine 2 pi times px plus qy, where p and q are integers. So pq is in z2. So that what are the eigenvalues for which this is eigenfunction? You just differentiate twice with respect to x, with respect to y twice, and add up. You see that it is 4 pi square into p square plus q square. That is the eigenvalue for the negative Laplacian. So you get a minus, but I look at negative Laplacian. So 4 pi squared n, where so the eigenvalues are 4 pi square n only if for those in positive integers n which can be written as a sum of two squares. If you cannot write n as a sum of two squares, then it's not an eigenvalue. Okay, so for example, 7 is not a sum of two squares, whereas 5 is a sum of two squares in many ways, 2 square plus 1 square. It's also minus 1 squared plus minus 2 squared if you want. So it has a multiplicity. In fact, what is the multiplicity? You are looking at exactly this describes the multiplicity also. So you have to look at those integer points pq in Z2 such that p square plus q square is n. That means that this lattice point lies on the unit circle. Okay, so this so when one studies this Laplacian eigenfunctions in the torus, number theory naturally enters because this connection to sums of squares of integers. So an eigenvalue is only, 4 pi square n is an eigenvalue if and only if n can be written as a sum of two squares. And also the multiplicity depends on the lattice point, how many lattice points there are on this circle. And that is quite a non-trivial point, how it changes as n changes. It's a bit wild, it's a wild function. Okay, so these are the two examples. So before going to the random situation, let me just recall what is known about nodal sets and so on in general. So there is a lot of study on this. So I have just summarized some rather deep facts in short. So in general, if you take eigenfunctions of a Laplacian on a manifold with these eigenvalues, there is a one of the things that we will be interested in is how many nodal components are there. For example, here. So here you see a small, in the middle you see a small black component. That is one nodal component. Here there is a white component. That's a small component. Whereas here there is a black component which is a bit larger. And there are much larger black components. So the counting. So one of the things that one is interested in, how many nodal domains are there? So the motivation comes for this as well as for this sign change thing. If you want, the simplest of all these is the Sturm-Liouville theory. In basic differential equations class, we see Sturm-Liouville theory, where you have these eigenfunctions and successive eigenfunctions, the zeros interlace. So that means it changes sign n times. The nth eigenfunction changes sign exactly n times. So that gives you a kind of picture of what these eigenfunctions look like. So one would like such a picture in higher dimension. And one way of it is actually true. That is the Courant's nodal domain theorem, which says that the nodal set of, if you look at the nth eigenfunction, okay, there is a little bit of subtlety in saying the nth eigenfunction, but for a moment, let me make the statement and then clarify. You take the nth eigenfunction, it has at most n components, okay? The nodal set, I haven't actually defined what is nodal set. What I mean is, the definition is later, I should have put it earlier. Nodal set means you look at the set where it is not zero, so it is either strictly positive or strictly negative, and you take connected components. So this is a connected component where it is negative. Here, this white part is a connected component where it is positive. So that's what is a nodal component. And the nth eigenfunction will have at most n components. In Sturm-Liouville problem, it is exactly n. So here it is at most n. Actually, there is a slight typo here. Maybe I should start with 0 to say it is n. Otherwise, it may be n plus, no, sorry. This way it is correct. The first one is positive. It has only one nodal component. And the next one will have at most 2. The third one will have at most 3 and so on. So that is true, but it's not exactly equal. So there are examples, and there is a picture here. This is an example of this is on the torus, but it's a very high energy eigenfunction which has only 2 nodal components. Okay, so it's a very large eigenvalue. but the number of nodal components is only 2. So there is no lower bound on the number of nodal components in a deterministic sense, but there is an upper bound of n. This is a general fact of Coant, from 1930s. And this example that you can't get any reasonable lower bound, you can't go lower than 2. Everything is orthogonal to the first eigenfunction, which is positive. So everything else has to have at least 2 nodal components. Somewhere it's positive, somewhere it's negative. But you can't go lower than that. I mean, it can be as low as 2. So that is a general fact.
So Manju, I
Yes.
have a question, Manju.
Yes.
So for the spherical harmonics, it's like it should be upper bound of n squared, right? Taking into account
Right. I
multiplicities and
mean,
all
so
that.
there, right. So when I say n, that's I said I will clarify. I didn't. Thank you. So what do I mean by this? So sometimes there can be degeneracy and equality. So you have to count it like that. I mean, so you look at psi, it is somewhere. You have to see what is the largest number for which it is an eigen value. Okay. So when you are looking at spherical harmonics, so there is dimension 1, dimension 2, dimension 3. So when you look at this n into n plus 1, the number of eigenfunctions before that is the sum of this 1 plus 3 plus 5 plus 1 up to that point, so which is of the order of n squared. So in that case, psi n, I should not, an eigenfunction here should be called psi n squared in some sense. Okay, so you have to order the eigenvalues and look at it. So if there are no degeneracies, it's not ambiguous. But if there are degeneracies, suppose you have 10th, 11th, and 12th eigenvalues are same, but 13th is larger, then all of those three, that eigenvalue can have up to 12 nodal components. That's what I mean. I hope it's clear. Okay, so then Faber-Kahn is another very important fact, which is useful for us also. So every nodal domain contains, no nodal domain can be very small. Okay, every nodal domain contains a disk of radius 1 over the square root of the eigenvalue. A lot of things happen at the scale of 1 over square root eigenvalue, and this is one of the first indications. So the nodal domains, every nodal domain contains a disk. You can't have a very tiny nodal domain. If you just take a smooth function, it can have a isolated zero also. Very tiny point where tiny nodal domain. But here that's not the case. So it has an in radius of this much. And then there is this other big thing which has been studied a lot, and there have been recent developments much. It's about Yau conjecture. One of the things is, what is the length of the nodal set? What is nodal set? Nodal set is where the function is zero. So for example, here, these curves, rather than the green or white regions, the curves. And here, rather than the black or white regions, it's the boundary. That's a one-dimensional set. It is known that it is up to a few degenerate points, it is smooth. So you can talk about its length. So it's a general conjecture of Yau that for any smooth manifold, the length of the nodal set is of the order of the square root of the eigenvalue. In the sense that there are two constants, so that the length of that nodal set divided by the square root of eigenvalue is between these two constants. Okay, so that constant depends on the manifold and so on. So this was done long ago by Donnelly and Pfefferman for real analytic metrics, but in smooth manifolds, there was a lot of recent work of Logunov, Malinnikova, and so on. So there's a lot of the recent development in it. So this, I don't go into this. I don't know too much of this either. There are other experts in India who work on these things. So these are some general, as far as general things are known, this is what is there. But we introduce randomness. Okay, there are two reasons. First, let us say that because it makes things simpler. Random is actually easier than deterministic. So often. So this gives a lot of play, and maybe sometimes you can make more accurate statements or more precise statements, as you will see later. But let's say it is for convenience for a moment. So instead of looking at these, okay, in the torus and sphere, people understand the eigenfunctions well enough in a way, but we introduce randomness. How do you introduce randomness? For the sphere case, we define something called SRW, which is the spherical random wave. Okay, it's a random function. How is it defined? You take the eigenvalue corresponding to the, n into n plus 1. Okay, so it has an eigenspace of 2n plus 1 dimension, for which I will choose an orthonormal basis, psi minus n up to psi n. That's a standard way to indicate them, but you choose any orthonormal basis, it does not matter. Then we take a linear combination of these eigenfunctions with Gaussian coefficients. So I did not write here. Okay, very strange. I haven't written here. Xk's are IID Gaussians. Okay, so Gaussian random variables. So I take a linear combination of this with random coefficients, specifically Gaussian. If you take IID Gaussian, then it is true that this does not depend on which orthonormal basis you take. This is the orthonormal invariance of Gaussian measure. You take Gaussian measure and Gaussian random variable, rotate it, it will still be Gaussian. So that is the reason why you take Gaussian. And this is just a scaling to no importance to this. So this is what we call the spherical random wave. Instead of studying deterministic functions, we study this random functions. And then there is maybe more precise things that one can say. And in fact, it's possible to say some things. Then on the torus, we can do a similar thing called the arithmetic random wave. So the arithmetic comes from the fact that sums of squares problem is there in that. So what do you do there? Again, go to an eigenvalue. So you write n as a sum of two squares. You may remember, I'll keep recalling this sometimes. The eigenvalue corresponding to that is 4 pi squared n. If n can be written as a sum of two squares, and the eigenfunctions are indexed by these lattice points on that circle, p square plus q square equal to n. And earlier I had written cosines and sines, but you can write it as a complex exponential and take a real part. It's the same thing. So here again, I take a Gaussian linear combination. So it's actually, don't worry about this real part and all this complex. It just means exactly like here, I take an orthonormal basis for the set of real eigenfunctions of this eigenvalue, and I put IID Gaussian coefficients and then take a linear combination. That is what we call the arithmetic random wave. Okay, that's a random function on the torus. So this picture was actually a random function on the torus. This is an example of that. Okay. Why Gaussian is natural? One reason I already gave, it is independent of the choice of basis. Otherwise, there is no eigenspace is well defined, but eigenfunctions, orthonormal basis for eigenfunctions is not well defined. So if I were to put some other random variables, you can ask why this orthonormal basis, why not some other? So with Gaussian, that question doesn't arise. So that is one reason why we always do Gaussian. Of course, first thing to try is Gaussian. That is the easier one. Second is that once you have Gaussian, there are very nice properties of Gaussian random variables. Okay, this is one thing I'm going to assume. I'll try to not assume much probability knowledge, but I'll assume people know what are Gaussian random variables, because at least that much I need to assume. Okay, but so Gaussians, linear combinations of Gaussians are Gaussians. So that is one of the basic things we learn. So for example, if I fix an x and look at this random function value, it is a linear combination of these Gaussians xk, right, with the coefficients psi k of x. So it's the value at a point is a Gaussian random variable. Not only that, if I take the derivative at this point, some gradient, say first partial derivative, second partial derivative, multiple partial derivatives, they are all linear combinations of the same Gaussian. So all of them are jointly Gaussian. So that is another good thing about this. Partial derivatives, etc., are also Gaussian. There is yet another nice property of this specific thing, that is that they are stationary under isometries. So the sphere is naturally, there is an orthogonal group acting on it, and these random functions respect that. In other words, if you take this random function, if you look at this picture here, if you rotate it, you will not see any difference in the portrait of the random function, because that is actually stationary in a statistical sense. If you don't know what is stationary, just ignore that. But these are two of the objects that will be there in this talk throughout this talk: the spherical random wave and the arithmetic random wave. Okay. But this is not the only reason why we introduce that. Actually, randomness comes from deterministic situations in many cases. So here is the reason why randomness is actually sometimes essential. So this is the famous Berry random wave conjecture. It's an open question, of course. In 70s, Berry came up with this idea that when you study large eigenvalue eigenfunctions, then you naturally come to a random function that is called the random plane wave. Okay, so more precisely, if M has constant negative curvature, then you take the eigenfunctions and let go to high energy eigenvalues, that is high eigenvalues. Then this function, there is nothing random about it, but on small regions, you take some point and look at it on a scale of 1 by square root of the eigenvalue. So you take some large eigenvalue, but look at it on a small piece of patch of the manifold, a neighborhood of a point on the scale of 1 over square root of the eigenvalue. Then on most points, it will look like a particular random function that we call the random plane wave. So this is called Berry's random plane wave. So randomness arises from deterministic situations in a natural way. What is this random plane wave? This is the third object that is there in this talk. So this is the most natural random measure on the space of solutions to this is on, these are functions on the plane. Okay, this random plane wave is a function. These functions are on the plane and they satisfy minus Laplacian f equal to f. That means eigenvalue is 1 for the negative Laplacian. So what is this random plane wave? The simplest way to think of it is like this. It is, you take these waves. Here I have taken complex wave, but I take a real part later. So you can take cosines and sines if you prefer. So you take a random wave. What is omega k? Omega k is a unit vector in the plane. Okay. Then this is a complex wave. This is a wave in the direction, in that direction of unit frequency, because it has absolute value 1, the frequency is 1. So what it is it's a superposition. I take a superposition of unit frequency waves in all sorts of directions. So I take it in all n directions here uniformly around the circle, but with Gaussian coefficient. So the amplitudes are random, but you take it in all directions. That is what the random plane wave is. So what Berry is saying is really that these eigenfunctions are like a superpositions of waves going in every possible direction, but the amplitudes are looking more and more random, like IID Gaussians. Okay, so this is the physicist's way of describing this random function, but you have to let n go to infinity here. The probabilist way of describing the same random function is without any limits, as the mean zero Gaussian process on the plane with spectral measure uniform on the unit circle. What it means is that you have a Gaussian random function. You have a random function on the plane which is Gaussian. That is, all the values, derivatives, everything will be Gaussian. And the mean expected value at any x is 0, but the covariance is given by this J0 of absolute distance between x and y. What it means is J0 is the Fourier transform of the uniform measure on the circle. So that's why I say that the spectral measure is uniform on the unit circle. So this random plane wave is the Gaussian process on the plane, which this is just you can think of this as a formal description of this. As n goes to infinity, instead of n uniformly chosen directions around the circle, you have all the directions in the circle together. And you have a kind of random superposition of those things. That is what this is saying, random plane wave. Yet another way of describing it, which doesn't indicate what it is, but it is a clear way of defining it, is as a random series with random coefficients. So you take these Bessel functions with index n. And in polar coordinates, you write this j mod n of r e to the I n theta and take them with IID Gaussian coefficients. This gives you back this same random function. So that's another way of thinking of it. Okay. So this is the reason why we are interested. One way randomness creeps into the problem. Okay, actually here I have made a remark that from probabilist point of view, there are lots of stationary random waves. For us, for probabilist, there is nothing special about this random plane wave. You take any symmetric measure on R2, there is a Gaussian process whose covariance is given by the Fourier transform of mu at x minus 1. Okay, so here the random plane wave was exactly the same for the uniform measure on the circle. But this we have it for any measure. So why particularly, what is special about the random plane wave? We don't know whether there is anything special. It is geometry which is telling us that we should consider that. This consideration of random plane wave came from considering Laplacian eigenfunctions and so on. So if mu is not uniform on a fixed circle, then these functions will not be eigenfunctions, but superpositions of eigenfunctions with different eigenvalues. So there is no PDE connection in that case, which is why I said I don't know whether there should be a PDE connection or not here. The state of the matter today is that there are some results known for the random plane wave, which are not known for other stationary random waves. So in that sense, PDE has been, I mean, the PDE connection exists, meaning there are results, but are these results really not valid for other random functions? We don't know. Okay. Okay. So it was rather longer than I intended introduction, but what I want to give in the rest of it, probably I will skip a little bit, is I summarize what is for the overview of the rest of the talk. I have introduced three random functions. One is the spherical random wave, which is random spherical harmonics of degree n. You take a superposition with Gaussians. Another is the arithmetic random wave. You take again for cosines and sines with lattice points in a circle and take Gaussian linear combination. Another is the random plane wave, which I just described. These are the three things. What are we interested about these random functions? One can study many things. One is you look at the set where the function is 0, that's the level set, and you may study the length of that nodal set. That is one thing. That's a random quantity. You may be interested in some things about it. You can ask about the number of nodal domains. How many nodal domains are there? That means nodal domain, as I said earlier, is connected component of the complement of the level set. So you take the connected component where f has the same sign, positive or negative. That is called a nodal domain. How many nodal domains are there? How many of them are simply connected? How many of them are doubly connected? What is the structure of this connection? All these questions can be asked. So what is it that you want to know? These are random objects. So what is it we want to know about them? Whether it's the length, let's just stick to these two things, length of the nodal set and number of nodal domains. You can ask what is the mean value, law of large numbers type question. What's the expected number of nodal domains, for example? You can go further beyond that, ask what is the variance and ask whether there are central limit theorems for the quantity, for the random variable here. And third is exponential concentration. These are the things that I will talk about. There are other things which I marked in red, which I will not talk about. I think they are not too much of interest to PDE people, maybe. Especially if there is no background, it may not make sense to talk about percolation and discrete setting is one can do all this on graphs. You can define graph Laplacian and so on, and you can study things on graphs. But, well, I'll stick to the continuum. Okay, so are there any questions or anything? So what I go on to now is, I will go on to these three questions, mean, variance, and exponential concentration. I may end up covering only two of them. So I will talk about these things. In all three contexts, I want to tell you it's a survey talk, by the way. So there is some results of mine also, but it's a survey talk of what we know about these things. Are there any questions or comments so far? Okay, so if not, let me go on to this one. So the mean, and so mean behavior and the law of large numbers. So what we are interested in is like expectation of the length and expectation of the number of nodal domains. So let's ask that question. So if I have a random function like that spherical random wave, or the arithmetic random wave, or the random plane wave, how do I calculate the mean nodal length? Okay, so that is the question. Mean nodal length, can we study it? So the thing about the nodal length as opposed to nodal domains, which I will come to, counting nodal domains, the nodal length is a local quantity. Okay, what is local quantity? Local quantity means if I take the, let's say we are working on the sphere and I cut it into 10 pieces and give you the pieces, you can look at the nodal length in each of the pieces and then add up to get the nodal length, right? So it's a local quantity. That's why it has an integral formula. So this is called the cat's race formula in probability. It's really the Covariant formula. So what the Korea formula says is that if f is a smooth function on a domain in R2, so here I'm writing it in generality. So then there is a formula we can write for the length, which is basically you take the delta function where fx is 0. So you look at the 0 level set of f, but it is, you want the length of that, you have to multiply it by the gradient and take the integral. Okay, what this means is really this. So you look at f where mod f is less than epsilon, and then take the integral of the gradient, norm of the gradient of the function on that, and integrate over the whole domain. And then let epsilon go to 0. That will give you the length. Okay, so I assume this is probably clear to most people. So in some places I do explain why you need to put the gradient, because the thickness of this mod f less than epsilon, if you look at the 0 locus, the thickness of the mod f less than epsilon is like a strip, but the thickness of the strip is not uniform. It depends on the gradient at the point. That is why to compensate for that, you have to put in the gradient. So once you have this formula, it is in principle possible to, if I now take a random function, capital F, okay? This is for just a deterministic function. We can write this kind of formula. You need some conditions, but it is true, let's say. For a random function, we can use this to calculate mean, variance, higher moments, everything. In principle, we can write. How? You just put the expectation through this formula. Okay, if I want expected number length of the nodal length of some random function f, how do I calculate that? Well, you put the expectation in this formula. You have to justify the limit and expectation interchange, but modulo that you get limit epsilon going to 0. Expectation of, instead of writing this in the integration domain, I just put that as an indicator here. Expectation indicator mod fx less than epsilon times the norm of the gradient. You take that expectation and integrate over the domain, then you get the expected total length of the random function. You can also write for the second moment. Well, you have to take two of these quantities, multiply, so you get a double integral actually over omega square, and you get the product of indicator mod fx less than epsilon gradient fx times indicator mod fy less than epsilon gradient fy, and you take the expectation of that and integrate over the omega cos omega. So, and so on. You can go on forever. You can write all the moments. That's okay, but usually you cannot do much with this formula. It's very complicated. You can imagine why. See, this fx is to, what does it take to calculate something like this? Well, fx is a Gaussian, fy is a fx, fy. Gradient has two parts, two partial derivatives. Gradient fy has two partial derivatives. So there are 6 Gaussians here. 1, 2, 2, 4, and to 6. There are 6. This expectation is over a 6-dimensional Gaussian random vector. And then you have to calculate that and integrate. It's fairly impossible. So it becomes very difficult. But the first one is okay. So I'll just summarize the results here. So how do you do the first one? The first one turns out to be easy. So I show it here for the random plane wave, for example. So for the random plane wave, you take some, it has infinite nodal length if you look at the whole plane. So you look at some compact region like 0, 1 square. According to the formula that I wrote just now, expected length of the random plane wave inside this square will be an integral like this. Is the expectation, I wrote here in a certain way, expectation of this indicator times the norm of the gradient, and then you have to let epsilon go to 0. With a little bit of justification, you can write it in this form. It is the density of fx. So you are looking at a point x. At that point, fx is a random variable. F is your random plane wave, okay? So your random function has a density, fx has a density at the origin, and that is this quantity, and this is the expected value of the norm of the gradient given fx equal to 0. This quantity is the same as this. I don't want to explain why. It's a simple manipulation of conditional probabilities. So you get this. So what you need to know is the density of fx at a point and the conditional distribution of gradient f at given fx equal to 0. This is easy to do, and I have written out the calculations here. For example, for the random plane wave, at every point, fx is a standard Gaussian, so its density is 1 by square root 2 pi at 0. And it turns out that because of stationarity, at a given point, fx and gradient are actually independent. So the calculation really simplifies, and you can calculate the expected norm of the gradient also quite easily, which turns out to be 2 root pi. So overall, this turns out, actually I have written something wrong here. It is 1 by root 2 pi into 2 square root pi. So this is wrong actually. So from this line to next, I have made a mistake in there should be a multiplication by this 2 square root pi. So with that, one can calculate the mean nodal length for all these three cases. In all three cases, the answer is the same. The answer is 1 by 2 square root 2 per unit area. The expected nodal length is 1 by 2 square root 2 per unit area. So in the case of sphere, you will see that it is 1 by 2 square root 2. The total length will be 1 by 2 square root 2 into the area of the sphere is 4 pi. There is another parameter which is the square root of the eigenvalue. So it is actually, yeah, it is 1 by 2 square root 2 per what? Per 1 by square root t is the scale which I said you should look at. So in that sense, this is I would say that all these three answers are the same. So in the arithmetic random wave also you get 1 by 2 square root 2 times the square root of the eigenvalue. When you're looking at a high energy eigenfunction, you can think that your space has expanded by dilation of square root of the eigenvalue. That's what it is. Or your unit length should be thought of as 1 by square root of eigenvalue. That is what is here. So this is how you study the mean of the nodal length. So it is not too difficult actually. It is an easy one. It's a nice application of the covariance formula. That's all. But mean nodal count is a completely different ball game. Okay, mean nodal count is a totally different ball game because it's not a local quantity. Suppose again you think of this random function like this here that I had here. Suppose I cut the sphere into 10 pieces and give you 10 pieces to 10 of you and ask you to count the nodal domains. You cannot put together the answers from this, right? I mean, it is very hard to make out. So in fact, you see, right? I mean, so this is the usual problem. I mean, this is how the kids' games are there, right? I mean, there are many children. I mean, when you're kids, there are these type of there is a maze and you have to draw a line from this entrance to the exit or something like that. So these problems can be quite tricky because when you look at a picture, it's even hard to make out whether 2 points are in the same nodal domain or not. 2 points may be very far off, but maybe in the same nodal domain. But that is the tricky part. So it's not so easy to make out. It's a non-local quantity. So you cannot expect any integral formula of any sort up for this. You have an upper bound for Cohen's nodal domain theorem, but that is just a crude upper bound. There cannot be any deterministic lower bounds. So there is a general thing that tells you how to answer this question. So if you look at a stationary random function, you just think of the random plane wave. This is a random function on the whole plane. It has the stationarity property, which is that if you translate the space, then the random function looks exactly the same. So if you want to translate the random function, then it looks statistically the same. In such a case, by just and under some conditions, namely if the spectral measure has no atoms. So in case of random plane wave, the spectral measure was uniform measure on the unit circle. It has no atoms. In such cases, there is what is called ergodicity. Okay, the whole process, so this measure preserving transformation, namely translations, is ergodic on this space of Gaussian measure. So this is a famous theorem of Maruyama, Gernander, and Fomin. Because of ergodicity, this problem kind of becomes trivial. From ergodicity, one immediately gets the conclusion that any quantity you look at, it has nothing to do with nodal domains, but specifically for number of nodal domains in a large area, if you divide by the L square, so number of nodal domains in 0L square divided by L square will converge to a constant. It can't be some random thing. Ergodicity tells you that limit has to be a constant, and that constant is some kappa. Okay, so just this is a general Birkhoff's ergodic theorem conclusion that you have a law of large numbers, and the expectation of the number of nodal domains by L square will also converge to the same kappa. So this is general consequence of ergodicity. But that doesn't always answer the question because this constant can be trivial sometimes, infinity or zero. Here, it turns out it can't be infinity, but it can be zero. And you can put some additional conditions on the Gaussian random function, which ensure that the constant is not zero. So there's an old work of Malevich in which she said that if the covariance is positive, then kappa is not zero. More recently, Nazarov and Sodin, who are among the stalwarts in this field, they found more general conditions that if the spectral measure is not too sparse, then it is this constant is positive. It's very general. It definitely applies to the random plane wave, and there is a limiting constant, which is usually denoted Nazarov-Sodin constant, but its value nobody knows. So there is a constant. So the number of nodal domains in this is actually constant times L square, but nobody knows. The same constant shows up for the sphere also. So in random plane wave, it is CNS per unit area. So in a large constant 0 L square, it is CNS times L square. If you look at the spherical random wave, this is the example that I had in the beginning. Here, if you ask what is the number of nodal domains here, it is n squared. This is what Kaushik was saying. It is n squared when I am taking the nth random function, n squared times a specific constant, which is actually the same Nazarov-Sodin constant that you have in the plane. So in CNS times n squared. Okay. So this is something that Nazarov and Sodin proved, that the number of, so the upper bound tells you that there can be at most n squared. In fact, 1 times n square, I think. So this constant is less than 1, but there is no respectable lower bound for it. We know it is positive. It is embarrassing to quote any actual lower bounds. It is they are very tiny from the proof. So on the arithmetic random waves also, it is in a generic situation, it is the same constant times the dimension of the space, but there are sequences along which you get different constants. So I may later talk about it. It depends on how the lattice points are distributed on the circle of radius n. So depending if the lattice points are somewhat uniformly distributed on the circle of radius n, you get the first behavior. But there are cases where the lattice points are distributed very widely on the units on the circle of radius n, then the constant is different. So this is what is known about the mean nodal count. So about the proof, all I can say is upper bound is from Cohen's nodal domain theorem, but one can get better upper bounds by looking at some nodal quantities. I mean, some local quantities. So you cannot count nodal domains. There is no integral formula. But for example, every nodal domain has to have a local maximum or a local minimum, right? So by counting number of critical points, you can bound the number of nodal domains. Each nodal domain has to contain a critical point. So there are other critical points one can look at. So I did some calculations like that once, but there is also old work of swirling. So you can get good bounds, not good, some decent bounds for the expected number by doing that sort of thing. You won't get the exact constant. But the lower bound is non-trivial, and this was done by Nazarov and Sodin by saying that you take a large region on the sphere, for example, of the length 100 over n. N square is the eigenvalue, 100 over n is the right scale, 1 over n is the right scale. So there is a positive probability for that large disk to contain one nodal domain. So once you show that, you can cover the whole sphere by many n squared such disks. Okay, and then consequently you get a constant n square many nodal domains. So that is the idea. So you show that locally it is possible to have a nodal domain in a small region. Then in expectation, it will happen so many times in the big region. So that is all. So there are no good lower bounds, no. There are some other things which I will skip. So if you want to count the number of simply connected nodal domains, etc., there are such theorems. And Bourgain extended the Nazarov-Sodin theorem to some deterministic situation. It's some de-randomization. Okay, I will skip that. There is an interesting physics approach to this, which is it is not clear whether it is correct or wrong. But Bogomolny and Schmidt proposed a way to study nodal domains, and they propose exact formulas for this CNS. For example, they say CNS is 3 square root 3 minus 5 over 4 pi square. Okay, so that is from a percolation model. They have this prediction, you may say, or proof, physics proof. So their claim is, I mean, it was before the Nazarov-Sodin work. Their claim is basically that the Nazarov-Sodin constant is this 3 square root 3 minus 5 over 4 pi square. Now, all numerical work done so far, there have been very, very high precision numerical work. They all seem to disagree with this. So the constant is close to this. It's not exactly this. So one doesn't know what to make of this prediction. At least I don't know. So Dima Belyaev, who has studied a lot of this, says that the model that they used, which is a percolation model, I will skip that, is good for certain quantities. It can be taken as a good substitute for the actual model we are looking at, namely random plane wave or spherical random wave. But it is not good model for the non-local quantities such as number of nodal domains. So we don't know. It's a very bizarre situation that they have these exact predictions which are not, don't seem to be correct. Okay. Any questions or comments on this? Okay. If not, let me go forwards to, there are two other things I mentioned. So one is, this is the mean behavior of the length and nodal domain count. So there is another thing which is exponential concentration. So which is the following. So let's again recall the spherical random wave, which is the superposition of these spherical harmonics of degree n. So, and let Zn be the number of nodal domains. What Nazarov and Sodin showed, that part which I showed earlier, that the expected number of nodal domains is constant times n square asymptotically as n goes to infinity, that is an easy part of the theorem. They showed something very non-trivial, namely that even the typical value is like this. Okay, so probabilists always distinguish between typical and average thing. So what is the meaning of saying that it is typical value? It's not just on average that it is this, but Zn minus Zn divided by n square, it is very close to constant, this constant. Or in other words, with the probability it deviates from it by a delta is decays very fast with n, e to the minus n, with a constant that depends on this delta. So this is what is called exponential concentration in probability. It's a very large area of probability showing concentration behavior. This measure concentration phenomenon is very common in high dimensions, and this is one example of it. So this is a rather unusual example of it. Even if you are familiar with measure concentration, this is an atypical one for a reason that I want to explain next. So the exponent, when I talk about exponential concentration, it is this behavior I'm talking about, that there is this random variable which has a certain mean, but the probability that it deviates from its mean by a factor of 1 plus delta is decays exponentially in some parameter n, like this. Okay, so what is the, let me first summarize what else is known. This very few results on concentration of nodal count is known, and the original one is due to Nazarov and Sodin. And then there was a student of Sodin called Rosenschein. He had a good paper on the arithmetic case. So it's not entirely straightforward to transfer the results to the arithmetic random wave. So he did that same theorem on the torus. And then, so in IISc, there is a student, Lakshmi Priya. So she's graduating shortly, and it is as yet unpublished work, but she extended this considerably. So she extended this concentration behavior to random plane wave, which was not known. She also extended it to more general monochromatic random waves. What it means is that the spectral measure is supported on the unit circle. I described earlier, there are many stationary random waves, but you can take, instead of uniform measure on the unit circle, you can have some other measure on the unit circle. So she managed to show exponential concentration for such things also. And also for, even in the case of spherical random wave and arithmetic random wave, so if you see this result, it is counting the total number of nodal domains. But I could look at a very small part of the sphere and count the number of nodal domains in that small part. And you can ask for exponential concentration for that random variable also. So Lakshmi Priya has proved such things in shrinking domains. In exponential concentration in this spherical and arithmetic random waves. Okay, but one of the reasons I want to mention this exponential concentration is this is one situation where the PDE seems to be the only thing that works, meaning that the fact that these are eigenfunctions is actually important. The mean behavior, it was not important actually. You can extend it to all sorts of Gaussian processes. But this exponential concentration so far is known only for this kind of things, these monochromatic waves. I'll explain that. But first let me explain what is the what is the idea behind proving such a theorem. How do you prove concentration? So basic idea is for concentration comes from this fact, which is really isoperimetric inequality. Isoperimetric inequality and concentration are very closely related things. So in particular, there is an isoperimetric inequality on the sphere, which is exactly more or less like the isoperimetric inequality on Rn, where we know that for a given volume, the surface area is minimized by a ball. Similarly, on the surface of the n-dimensional sphere, there are spherical caps, which are balls in geodesic balls in the sphere. Those minimize this boundary area given the volume inside Sn. So that isoperimetric inequality leads to what is called Levy concentration. Paul Levy was the first one who did it. Immediately, it is more or less a translation of that. Tells you that if you take okay, so I got phi there and f here, this should be f. If you take a Lipschitz function on the sphere, then in the uniform measure on the sphere, most places the function value will be close to its median. Okay, so what this is, this mf is the median value. You think of it as some one number. It is one number. So any Lipschitz function is more or less constant on the sphere. Okay, the area of the region where it deviates from its median by a number t is very small. So that is the amazing thing about this Levy concentration. Okay, so how is that of any help for us? What we are looking at is this spherical random wave, right? So what is the spherical random wave? It is made of these coefficients xk's. There are 2n plus 1 of them. They are Gaussians. So it doesn't matter if I scale all of them by some constant also. That won't change the zeros of this. And we are looking at the zeros of this random function, right? So instead of that vector x, so there are 2n plus 1 coefficients x here. So put that as a vector and divide by its norm. So because they are Gaussians, that vector is uniformly distributed on the sphere in n dimension. So this isoperimetric inequality applies. But what is the function I want to look at? What I want to look at is a very complicated function of this random vector. So this is a point on the sphere, and the f I evaluated at this point is a complicated thing. What is it? First, I have to take that point and form this random function up to a scaling. I should look at its zero set, and then I should count the number of nodal domains. So you see, it's a very complicated function of that, and it's not Lipschitz. So you cannot apply Levy concentration here. That's why I said that this is an atypical situation of concentration behavior. But what Nazarov and Sodin showed is that even though it is not a Lipschitz function, it is almost Loyer semi-continuous, which is this is a very non-trivial fact, that this random function, for the random function, it's almost Loyer semi-continuous, and then you can plug it back into this Levy concentration and get the concentration behavior that they got. So the non-trivial part was showing the almost Loyer semi-continuity of this map, taking these coefficients to the number of nodal domains of the vector. So it's not everywhere Loyer semi-continuous. There are exceptional regions you have to throw away, and after that, what is left there, it is Loyer semi-continuous. So, and here is where the PDE comes into play, that to prove this Loyer semi-continuity, they have to use two things. One is Faber-Kern inequality, that lower bound on the in radius of nodal domains. Okay, and nodal length. They also use another fact that the nodal length of any spherical random harmonic is at most 2n. This is a known fact. Comes from the fact, I mean, it's very closely related to the fact that degree n polynomial can have at most n roots, right? So it's just comes from there. So this is where the result uses actually the PDE part, and nobody knows concentration for other sorts of things. For example, here is an open question. So instead of taking the spherical random wave at the nth level, suppose I take all the first n and take a convex combination of this. That means I'm not using just the nth degree spherical harmonics, but all spherical harmonics up to degree n. Then no one knows how to prove exponential concentration for the number of nodal domains of this, because this is no longer an eigenfunction. This is a superposition of eigenfunctions with different eigenvalues, and this doesn't work. So what Lakshmi Priya has done in her thesis work is that she had to do quite a bit of work to go to the planar situation, but she has not managed to break this question of requiring the Faber-Kern inequality. So she also requires that these be eigenfunctions on the plane. So she works with random plane wave or other monochromatic waves. And but one difficulty that she had was that this deterministic length bounds you don't have in the plane, and she had to establish probabilistic upper bounds for that. So after doing that, one can carry out the proof of Nazarov and Sodin. So this is how this concentration business works. So the last part I had in mind was variance and central limit behavior, but I will just skip. I'll tell you what I was going to say, that the variance of the nodal length can be calculated actually. It is actually much more difficult, and just this table tells you what the variance is for the nodal length in different situations. For nodal count, variance is a largely open problem. Only recently there has been some development on the lower bound for variance of the number of nodal components. But for variance of nodal length, it is doable. It's kind of difficult, but it is known in some cases. And one of the notable features is that the variance is actually quite low compared to what one would expect a priori. So for example, in the random plane wave, the expected number of nodal domains per area E in 0 E square is E square, but it's 4 o'clock. Variance is only log of E. And similarly here also it is kind of small. Okay, so maybe I will skip the rest of it. I had a few slides about the arithmetic random wave where the number theory enters the picture and makes a difference to what the variance is, but I will skip that. And okay, thank you for the attention.
Thank you, Professor Manjunath, for the wonderful talk. Now I request all the participants to put their queries in question and answer box, or they can raise their hands so that I can open their mic and you can ask the question directly to Professor Manjunath.
So Manju, I have one question, which is that so how do you compare, so that earlier one of the results is in radius is at least of size 1 over the square root of eigenvalue, right?
Yes, yes.
And then in
That is for
the
equality, yeah.
right, and then in the random case, for instance, Nazarov Sodin or Lakshmi Priya's work, so you said that the idea for concentration is to look at a very small region, like say of scale 1 over n, and to show that there is an entire nodal domain contained in that small, that whatever, right?
No, for the expectation, you mean. So that was for the expectation, right? So you mean for lower bound for expectation here, right?
Oh yeah, sorry, yeah.
So this is only with a positive probability.
Okay. So, but is there anything known in general, like in the random case, one can say something about the size of the
So no,
nodal
the
set?
way this works is actually, so if you look at, for example, you take the case of the sphere. You produce one eigenfunction which has this property, not random. You just produce one eigenfunction. For example, there is this thing called the zonal spherical harmonic, whose nodal domains are just latitudes. Okay, so it is peak. It is very peaked at the north pole. So the zonal spherical harmonic is a specific spherical harmonic which is peaked at the north pole, and it has a nodal domain within a distance 1 over n of the north pole. Okay, and then it has more latitudes where it vanishes. It doesn't matter. Once you find one such function, you just ask the probability that your random function is very close to this particular function in a neighborhood of the north pole. Then you can show that your random function will also have that nodal domain, a slight perturbation of that nodal domain. That is how you get this kind of result.
Okay.
So I have a question.
Huh.
Yeah, so in the theorem of Sodin, So that result, is it optimal? I mean, in the sense that
Here, this one?
Yeah.
Yes, they show the lower bound also is exponential in n. And it's a good question in Lakshmi Priya's case. Here it is known that it is, I mean, even you can take, for example, actually any example you take will give you the counter example. So it is as usual in probability. Typical one has this behavior, but you take a specific one. For example, the zonal spherical harmonic. It does not have anything like, I mean, this many. It has n nodal domains or something like that. It is very far from this anyway. So that will do as an example. And you can show with exponentially small probability, you can be close to this one. So like that, you can get lower bound. So the probability for this is at least e to the minus n. In Lakshmi Priya's problem, where she is working in the plane, so I said she has the same lower bound in many cases, but in some cases she does not have matching lower bounds. For example, certain monochromatic random waves, the upper bound and lower bound, she has not yet been able to match. So there is a question. When the measure is not nice, it's a fractal measure, then the upper bound is not quite like this n, but something worse. And then there is a mismatch of upper and lower bounds. So yeah, that's the answer.
So,
did that answer your question?
Yeah. Yes, yes. Okay, so are there any more questions? So in case there are no more questions, let us thank Professor Manjunath again for this wonderful talk. And we meet on next Thursday for the talk of Professor Eric Shaw on controllability of waves and geometric Carleman estimates. Thank you, Professor Manjunath, for the wonderful talk again.
Thank you. I'm sorry there is not too much PD. I'm
No,
not
no, no,
sure.
it was excellent.
Okay.
So yeah, so and I request all the participants to leave the platform now. And thanks again. Yeah, thanks a lot.
Okay. Thank you, Prasenjit.
Thanks a lot, Manjunath.
Yeah, bye.